This is my Lab 3 for the magnetic field of permanent dipole moments. The purpose of this experiment is to compare predicted and experimental values of magnetic field in order to display the distance dependence and also measure on and off-axis magnetic fields resulting from a small bar magnet. The Biot-Savart law is one of the main physics concepts used in this lab, as well as further understanding of magnetic fields. The procedure uses a small bar magnet and some basic household supplies in order to find the distances between the magnet and the magnetometer, and each of these at different measures of magnetic field. The experimental setup included downloading the magnetometer app onto my smartphone. You can see a screenshot of what that looks like with the magnetic field at the top and then the X, Y, and Z components below that, all in microteslas, later to be converted into teslas. You can also see a picture next to that with the representation of where the actual magnetometer chip in the smartphone is. This was done through the procedure given in the lab instructions. Below that, you can see a picture of my bar magnet with the ruler, and it's located down the ruler a little bit because of the metal piece at the end of it, and I didn't want it to mess with any of the measurements. So this distance was accounted for in each and every measurement done. Here you can see the three mathematical equations that will be used in this experiment. First is the distance dependence equation, which will be used to show that as distance increases, the magnetic field decreases. So we're going to measure the magnetic field at multiple distances, and that'll be displayed in the next slide. And then using the second equation, we will graph the natural log of the r and b vectors for these differing distances. And then you can use that equation also to solve for the n and k values. And the third equation, the Biot-Savart law for the magnetic field, will be used later in the coding section of this lab. In this slide, you can see the measurements taken for the distance between the magnetometer and the bar magnet when the x component of the magnetic field was equal to 20, 70, 120, 170, and 220 microteslas. The Excel sheet was then used to calculate the averages of these, and then further in the bottom left, you can see the natural log of both the R and X component of magnetic field, then graphed in a graph as shown on the right. When the line equation of this graph is then also compared to the second equation in the mathematics slide, you can see that the n value is equal to the slope, and then the 14.076 that you see is used to calculate k, and then also these values can be used further to calculate the value of mu, which is the magnetic dipole moment. For the off-axis measurements, the first step was to find the distance between the magnetometer and the magnet when the x component of the magnetic field was equal to 100 microteslas, and then move the magnetometer perpendicularly to the first location, the same distance, so that the d distance would be that between the magnetometer and the magnet at a 45-degree angle. Then repeating that 3 times and noting down the x, y, and z component as well as the net magnetic field. Those were averaged and then used to find the measured magnetic field at a 45-degree angle. And then that was used in comparison with the computed magnetic field as shown later. So here on these next few slides, you can see the code used in this lab to calculate the off-axis magnetic field. Here you can see that it is defining constants, functions, and observation locations and all that. Specifically in line 32, you can see how the equation that is highlighted on the right, the Biot-Savart law mentioned earlier, is defined. Here you can see the creation and the defining of the arrows, the 2 on-axis and the 4 perpendicular or off-axis arrows. And then this last section is the off-axis magnetic field at a 45-degree angle. So here you can see the output of the previously shown code. The white cylinder is the bar magnet, orange arrows on-axis magnetic field, and blue arrows are off-axis magnetic field. It's important to note that there should be a green arrow at 45 degrees representing the magnetic field at 45-degree angle. It's written in the code as highlighted below, but for some reason it's not showing up. This may be an error with GlowScript or something I'm not noticing. But you can see in the output at the bottom right that there is a vector coming out for the B at 45 degrees at distance D. So there is something happening, but for some reason the arrow isn't showing up. You can also see that this vector is what is used previously to compare to the measured value of B, with this computed value. So through this lab, we can make some conclusions and some notes based on our observations. First, as distance r increases between a bar magnet and the observation location, magnetic field decreases. We call this distance dependence. Then, based on our model, we can see that on-axis magnetic field points in the same direction as the magnetic dipole moment mu, and off-axis magnetic field points in the opposite direction of mu. And the magnitude is also seen to be, or shown to be, about half of those which are on-axis. You can see that in the output of the model as well. Another important note is about the lining up of the magnetometer with Earth's magnetic north, and this is to decrease any chances of less accurate results or measurements. Thank you for listening.